All right, so we want to look at one other technique for solving differential equations, first order differential equations. We've talked about separable equations. We've talked about linear equations. We've talked about exact equations, and then today homogeneous equations. So you've got several things in your bag of tricks. Sometimes students worry that I'm just going to say, go and solve, and I'll say solve the linear equation to remind you what to choose. I won't make you just try a whole litany of things. That's not really fair to you to do it that way. So today we want to talk about one other idea, solving homogeneous equations, and don't focus too much on that word. It means some different things in mathematics, but when you see that for the purposes of our first test, is this technique that I want to talk about with you today. So I want to arrange things so that it is a function of y over x. And I'm going to actually use a substitution or transformation, if you will. And the transformation that I'm going to use is this one. V is equal to y over x. Really, if I kind of pretend that y is v times x, that implies then that v is y over x. But if I differentiate this portion with respect to x, so the derivative of y with respect to x is dy dx. Then I've got a product rule over here. So the first times the derivative of the second. The derivative of x with respect to x is nothing more than a 1. Plus the second, which is x, times the derivative of the first with respect to x is the derivative of v with respect to x. So this and this are going to be the substitutions that I use to solve that problem. So you want to keep those maybe in front of you. So the first thing we want to do is to rearrange things as a y over x term. Sometimes that's easily done, sometimes not. And then I want to substitute in for dy dx, this substitution, and solve the problem. Usually it becomes a really nice separable equation. Look at what I've called example 1. So if I want dy over dx, I need to first get these two terms one away from the other. It doesn't matter what you decide to move. Excuse me, I'll move this x squared term. Okay, so if I want dy over dx, then I can divide both sides by dx, and there it is, dy over dx. These go away. But I also need to get rid of this x squared term, so I'll divide through by a negative x squared. All right, on the left, I end up with a negative y squared over x squared, and then I'm just separating these two things into two fractions, so plus xy over x squared. So I'll leave that for you to think about the algebra for just a moment. Again, I've put both of these numerators over that same denominator, and then I also took care of those negative signs. Had I flip-flop things, otherwise I'd get an equivalent piece. All right, what I'm looking for is hidden y's over x's. So right here, this is the same as y over x quantity squared. And then this x will cancel with one of these. So I'm left with just a y over x equal to dy dx. So I've been able to arrange everything as a y over x or a dy over dx term. So now I can make a substitution. Everywhere I have a y over x, I can replace it with v. And everywhere I have a dy over dx term, I can replace it with all of this, which is a v plus x dv dx. And then this happens, I think, every time. I hate to say every time, but I think it will. Some of this will even add away. So the problem that I have now is a negative v squared equal to x dv dx. That's the problem that I now want to solve, and it's a separable equation. So if I multiply both sides by 1 over dv, but again, I think we saw this in some work earlier, maybe the first week. I don't have a rule for the dv's and dx's in the denominator, so I'm just going to literally flip over this entire equation. And I'll integrate both sides now. It always works out to be a nice problem that we can integrate. So this side, to do the integration, I'm going to move the v up. And then the other side fits a rule. So I have, if I integrate v to the negative 2, add 1 to the power and divide by the power, that becomes positive 1v to the negative 1. And if I integrate dx over x, that's our old favorite natural log. And then somewhere a constant of integration. All right, so I've kind of got that solved in terms of v. Unfortunately, v wasn't what I was looking for, was it? I'm looking for y's and x's. So let me substitute back in. So I know that v is the same as y over x. And if I'm dividing fractions, 1 divided by this fraction, that's the same as x over y equal to this. That's not very convenient to solve in terms of y. It's not a very pretty answer, but nonetheless, I think I'll keep it as my answer. Okay? So each time for these problems, we're making that substitution and then solving the resulting separable equation. Look at number 2. Same sort of idea. Let me move some things around. I don't know which is more convenient to move. I moved. I guess I'll move it like I did before. So this whole term is positive on the left. When I move it to the right, it becomes the opposite. So I just went ahead and applied that opposite there. Okay, and I need a dy over dx term, so I can divide both sides by dx. The other piece, I got to get a little bit more creative on, so let me just write out what's left. X minus 2y plus 1 equal to negative x plus y dy dx. So just another little trick there. As long as I do it to everything, this one product over here and each term over here, then I'm good to go. So I'm needing y's over x's, right? So let me divide every single thing in here by an x. All right, and as I look at that equation, I'm able to get a 1 here, a 2 times y over x. This term right here is troublesome, and so I just picked a problem, and I didn't pick a very good problem apparently. A negative 1, a y over x term, and a dy dx term. So I'm able to put a v here. I'm able to put a v here. It's this term that's troublesome to me. So actually that tells me that this is not homogeneous. And that was unintentional, but I'm not able to solve that problem with this technique. There's some other techniques out there, but we'll save those for another day. So I'll move on to example 3. Example 3, I'm looking at dx over dt. So the substitutions that I'm going to make is if I let x equal to vt, right? Then I'm looking for opportunities to find x's over t's to remake that substitution, just like I did y's and x's. and then dx dt is going to be equal to this expression. It's the same sort of idea except the change in variables there. So I've got a dx dt term. I can make that substitution. It's the right-hand side that I'm concerned about. So let's see what we can come up with over there. So I'm going to split this apart into two separate fractions. There's one. And here's the other. Both of those numerators over that same denominator. So we have dx dt is equal to x squared over tx plus t on the square root over tx. So let's see what kind of things we can do to simplify that. So in the first term, the x's are going to cancel. So that's what I needed to make my substitution, right? In the second term, the t's cancel. And actually, I'm going to think about that. Just got to get creative. Instead of x, let me rewrite that as the square root of x squared. Better yet, let me write that as this term. And so there is a t over x term. I can deal with that. And an x squared over x term. So that's going to be the square root of t over x quantity squared plus 1. Now, I know what you're thinking. I needed x's over t's, and now all of a sudden I've got t's over x. I can always take care of that. If, let me go way back up here. If I take the reciprocal, and I can even write that as v to the negative 1. So the algebra gets all involved here. So I can make a substitution for each of these pieces. So here we go. Dx over dt is equal to v plus t dv dt. That came from this portion. I have an x over t term, which is a v. And then I have the square root, and I said we could do 1 over v. Maybe I will leave it like that. That's a 1 over v squared. I'm actually wondering if I hadn't done the integration yet, so I'm just kind of thinking ahead. Maybe a common denominator is in order there. Who knows? So if I make 1, I'm sorry the algebra's getting all crazy, but 1 is the same as v squared over v squared. And so 1 plus v squared all over that same denominator. And then I can pull the same sort of trick that I just did. And maybe I'll be able to do the integration there. We'll see. So at any rate, I've got, with these v's go away. So I'm left with t dv dt equal to the square root. So if I multiply both sides by 1 over dv, and over here I'm left with 1 plus v squared v dv. But again, that's the same problem that I had a second ago. I can't integrate with dv's and dt's in the denominator. So let me take the reciprocal of both sides. And actually, let me go ahead and clean up the right-hand side. This is sort of like every integration technique you've ever used is coming back in these problems. So pause it if you need to and think about how I got to that answer, but I think now both sides will integrate. So if I integrate the left-hand side, that's the natural log of t. And I believe the right-hand side is a u substitution. So if I choose u to be 1 plus v squared, then the derivative is 2v dv. So I need a 2 in and a 1/2 out. So this now looks like 1/2 the integral of u to the negative 1/2 du. And if I integrate that, add 1 to the power becomes u to the positive 1/2 and divide by it. That 1/2 is still out there. This came from the integration. So those 2's are going to cancel out. So I'm left with my u to the 1/2 plus the constant of integration. Again, that might clean up a little bit. I'm going to leave it as that answer. All right, try the couple of problems that I gave you for homework there, and we'll talk about them later in the week.